Okay, so we're waiting for, is everybody there? More or less. All right, okay, let's start. Good morning. As you can see, I'm now full set. I look like a hardcore gamer, but it seems that the configuration is perfect now. You can hear me well. My connection should be super stable, and also at the same time, you get my cam and you get what I wrote on the tablet, so it should be fine. Is it the case for everyone, or do you have any issue listening to me or anything else? Looks okay.
No issues for me.
Yeah, it's fine.
Okay, perfect. So we're gonna start this session, of course, with your questions about the lectures, about the test form, about last session. So yeah, feel free to take the lead and ask your question if you have any. If it's clear, that's fine. I'm gonna just wait for people if you have some question.
I had a question, but I need to find the page again.
I'm confused how to do the second test form. I didn't about
the second exercise of the test form number 4. That's your question?
Yeah.
So so the question was to find the current through a specific branch. That's it, right?
Yeah.
Okay. Okay. So I can cross quickly this exercise if you want. Is it there is a specific circuits you cannot do, or this is just a general concept you didn't catch?
Just generally, I didn't understand how to do it.
Okay. Before starting with this, other questions, Nathan?
Yes, with the Canali theorem, I don't understand why you can, in the lecture, I don't understand why you can just disconnect some resistances.
Okay, this is just not, this is just a way to calculate it. So this is not what you used to do, like to find a current, you can disconnect this, but in such theorem, you are able to do it. So this is just a way to find it and demonstrate it. That's it.
Okay, thank you.
Other questions before starting with the test form? Seems okay. Just something I didn't say at the very beginning. What about the speed of this class? Is it fine, or this is too quick for you? Do you have enough time to get things, or do you need more time? Just let me know about the speed. Is it fine with you or not?
For me, it's fine.
Should I slow down at some point, or do you have? Normally, the way of working like this, and I forgot to say this at the very beginning, we are going to be in advance compared to other groups, which at the very end are going to leave you an extra session free, completely free. So the very last session of this class is going to be a la carte session, which is going to be a session where we're going to discuss working on past exam, working on specific concept, making small groups depending on what what are your issues or difficulty on specific concept. I'm going to create more groups so you can work specifically on concept or past exam or whatever you want to discuss. We can spend some time to make a sum up of the full class also during this last session. So with this way of working, normally we should have this free session at the very end. But again, I can adapt myself to reduce the speed to if you think it's too dense or not. No reaction? It means that it's fine with you?
Yes, for me it's fine.
Okay. All right, so let's start with this exercise, which is about the Kirchhoff law. So just to remind you, so when we discuss Kirchhoff law, in fact, you have two laws, which are the node law and the mesh law. The node correspond to current and the mesh correspond to voltages. So when we discuss a node, we already see that, but when you have a node, which is a connection between different wires, then if I1, I2, I3, I4, I5. So the deal is when you apply the node law, the sum of the currents entering in the node equals, so input equals the sum of the currents going out. In that case, entering you have I1 plus I5 plus I3 equals to I2 plus, sorry, I4. Then considering the mesh law, so let's say that you have a different kind of these type of circuits. Okay, so you have to detect what we call a mesh, which is just a connection between branches. This is a definition you found in the in your document. So here in such circuits, in fact, you have three meshes. You have one meshes here. You have one meshes there, and you have one large meshes. So it means that each time you can apply the mesh law in any of these meshes. So let's now put some points. And of course you can draw also some voltages. Again, for the moment it's arbitrary. So UCD equals to what is delivering by this voltage generator, let's say 5 volts. Then between these two, well, we can draw, of course, UDE, but you know that it's going to be equal to 0. Same here, if we plot UCA, it's going to be 0, 2, because they are just these two nodes here, these 2 points are linked only by a wire. Here it's different because you have a resistor, so it's UFE, and then UBF. Okay, I'm sorry, I forgot this one, UB and D. So now I've put on every branch the corresponding voltage. And of course, in any of these meshes here, I can apply the mesh law. So to apply the mesh law, starting from one point, then you do the surrounding. And so let's try to apply it in these meshes here. So you have UCA. So sorry, let's be clear. When you apply the mesh law, also you need to fix a direction, which means that now that all the voltages are plot, you're gonna say I'm gonna apply the mesh law in a specific direction following a specific orientation direction. So let's say we're gonna apply the mesh law going that way in this direction, rotating in this direction. And we're gonna say that everything that's gonna follow this direction is gonna be positive, just looking at the different arrows, okay? So I'm starting here, applying the mesh law in this A, C, D, B mesh, considering a positive direction in this direction, and I'm starting from here. So I have UCA. It's positive because I'm going that way, and this arrow has the same sign than this positive orientation. If this is, if you have some problem or if I'm not clear, please let me know. All right. So starting from here, I have UCA. Then I encounter this UCD voltage, which is in the opposite direction, correct? I'm going that way, and this arrow is in the other direction. So I have minus UCD. Then keep going in that direction, plus UBD, plus UAB equals to 0. This is the mesh law applying in this system, considering the positive sign in this direction. Is it okay for everyone, or do you have question on that?
How do we know in which way it goes? Like, is it written or do we decide it?
So it really depends. Either it could be written or either you have to fix this. And we will see this in the different exercise. Yes.
Okay, thank you.
So right now I fixed these voltages here. They were not written. I put the different arrows with the different direction, and then I apply the mesh law considering a specific positive sign in this specific direction. But all of this right now are arbitrary. I fixed everything, okay? So you can do the same exercise here, sorry. In this mesh here, you have U, so I'm starting from this point, going positive in this direction. I have U, B, D plus, sorry, minus, sorry, I'm doing, this is bullshit. Okay, so I'm going that way. So minus UBD minus UDE plus UFE plus UBF equals to 0. Does it make sense?
Yes, just a question.
Yep.
Why did you plot the arrows the way they are? Like, why does UAB go actually from BA, like from B to A?
So this is a convention. So if you have 2 points,
yeah,
UAB is always like this, with the arrow pointing toward the first letter A. Okay.
Okay, it always goes from right to left.
Oh well, if you want me to do the other direction, that's fine. This is just, you have to remember that the first letter is where the arrow is pointing.
Okay. And why, for example, I mean, why did we make these choices of arrows?
That's a good question. It's the same that Tiziana was asking. Right now, I'm just putting them arbitrarily. But then,
Arbitrarily. Okay.
sorry, arbitrarily.
No, we may. Yeah, I understand.
But sometimes it's going to be obvious, or at least smart, to put them in a specific direction. But we will discuss this after.
Okay.
Okay.
Thank you. Yeah.
Perfect. So with this in mind, now we are able to try to make the test form. I'm not going through all the exercise of the test form because this is a way for you to auto test yourself, because you already have the result of this test form. But I'm going to show you the thinking and how to handle this exercise with only one exercise, and then of course practice with all others and try to find the right result. And for the next session, of course, if you have some issue with this, we can go back again with this exercise. So let's pick the first one. So let's write in black. Let's make very thin. Here we go. So no, this is crappy. Okay. So I have this. And the question is, what about the current I have in this branch here, considering this full so R1, R2, R4, R3, and we are discussing the current here, this current there here. Okay, so the idea is to is this a way, of course, first to try to simplify this this circuit, considering the association of dipole we have seen last time. So we saw last time few way of simplifying circuits, and this is a good way of using it here. So this in these circuits, you can see that what can you say about the resistors? Can you add them or simplify them in some ways?
We can add R1 and R2, and we can also add R3 and R4.
Exactly. Why? So here you have a node, which means that, of course, in this branch, you have a current I, you have another current flowing in this branch, which is I1, and another current flowing in this branch that we can call I2. But this current is also flowing through R4, which means that these two resistors are in series and these two resistors are in series. So now back to the way we can simplify this exercise and the circuits. You have E like this, you have a resistor which is R3 plus R4 here, and you have another resistors here which is R1 plus R2. Okay, and we are still looking at the current flowing through these branches. You just substitute these two resistors in series by an equivalent resistor, which is the sum of these two. And now you know two laws from now, which are the node law and the mesh law. And here, the simple thing will be to apply the mesh law in this mesh here. Okay? So again, so you have some node, and the thing is to write the different voltages in between the terminal of the dipoles. So this voltages is already given, all right, coming from here, which means that we are in this direction positive, and this voltage generator is delivering a voltage equals to E and positive in this direction, okay? Then we need to consider writing a voltage in between the terminal of this equivalent resistor. So I can either put the arrow that way or also put the arrow the other way, okay? They're both correct. But remember that when you apply the Ohm law and you have a current entering in a resistor, depending on the direction of the voltage here, it's going to be either positive, if you consider this being what we call the receptor convention. So this is receptor convention. But if you decide to put it the other way, still correct, but this time it's going to be minus, being in the what we call generator concept or convention. I don't know if convention is the right, maybe standard will be better. Okay, so it's up to you. But again, to not be confused, I will advise you to always try to adopt the receptor convention, which means if you can, of course, try to put the arrow here in the opposite direction than the current. Okay, so we have everything in these meshes, which is current and different voltages. Then I want to apply the mesh law here. So let's do it quickly. Let's start from here. So I'm not considering, well, I can do this, but again, here it's not useful because the voltages here is 0 and the voltages here is 0. So in fact, in these meshes, I'm only considering these voltages and these voltages. So, yeah.
We can't see your mouse when you're moving it.
Oh, sorry.
Is there like a pointer or something?
Maybe, but since I am on the tablet, maybe it's not working. Sorry, I will try. Okay, I will take into consideration this. Sorry. So we are in these meshes, right? The problem, well, it's not a problem, but so you have 4 branches, 1, 2, 3. So let's say A, B, C, D. This AB branch, you know that the voltage is 0, okay? They are linked together by a single wire. Same for C and D, okay? It's 0. So of course, if you want, you can put an arrow, but this is useless. The only 2 voltages which are important here are this U here and this E here. So you can go for the mesh law. So starting from A, U goes in this direction. So saying that it's positive in this direction. Starting from A, I have minus U plus E equals to 0. which make U equals to E. But, so this is by applying the mesh law starting from A and going, sorry, in this direction. But even without applying the mesh law, you can say that these two, so you have C, D, you can, even from the scheme that U equals to E, because they are all pointing, they're both pointing in the same direction, and they both link A and B, which is the same node, and C and D, which are the same node. Does it make sense? I hope so.
Yes.
So then the idea is, what is U? Because of the receptor convention you apply, and because of the current I, which is entering in this R3 plus R4 resistor, you have I time R3 plus R4. And you can deduce that I equals to E over R3 plus R4. And we're done. Is it okay? So then you can practice. We're going to use always the same protocol, always the same thinking to try to solve this problem. So I'm going to stop here with this example.
Excuse me?
Yes.
Can you explain again why U is negative here?
So I'm starting from A, and I'm considering the voltage is positive when I'm going in this direction. And I said, going in this direction is positive. So I'm going here, I'm going in this direction, and now I'm facing this U, which is opposite in the direction I'm going, which is positive in this. That's why it's minus. Then I keep going in my meshes, and here in this mesh, I am facing now E in the same direction, so it's positive.
Okay, I think I'm just confused because under there's written like U is equal to Ri, but U isn't in the same way than I, and it's
exactly. So this is, yeah, sorry. This is the definition. So now let's keep doing it in the other in this meshes here, in this the other mesh here. Yeah.
Is the current entering R3, R4 the same as the current like going out of the resistance?
Definitely, yeah.
Okay.
This is the same branch, and in the same branch, they are receiving the same current I. This is why in the first, if we go back to the first circuits, this same current I here is entering R3 and is also entering R4. So you can add them, and of course, in the equivalent circuits, the one I redraw, the same current is entering the equivalent resistor R3 plus R4. And of course, going out here, I is also going here. You can plot the current I also here, but then enrich a node, which means that now you have another current I1 here and another current I2 here. Then if you fixed I2 in this direction, then you're facing a new resistor. This resistor from now doesn't have any voltages in between this terminal. You're allowed to fix these voltages in the direction you want, but a smart, well, it's not a smart direction, but if you don't want to consider an extra minus sign, the advice will be to consider the receptor convention, which is writing plotting the voltages in the opposite directions in the current. Then here you have another mesh law. And you apply the mesh law, and in this mesh law, starting from A, you can go in whatever direction you want. You fix the orientation you want, you fix the sign you want, and then you apply little by little every voltages you encounter in your meshes. Do you get that?
Yeah, that's clear. Thank you.
Perfect. So now let's try to apply this directly in the next exercise. So again, go back to the test form, try to do all the different exercises that now you have the full thinking of and understanding on how to handle this. And of course, next time, if you have some issue again with this test form, we can go back to this, or also you can drop me an email with where you are blocked, and I will help you. So now back to our exercises. We're gonna go through the next exercises, which is the exercises number 3, voltage divider. So exercise 3, voltage divider, and this is quite important to get as a circuit because this is very useful, and we find this multiple times in a lot of circuits. So this is just another way of writing a circuit, which means that this is more like an electronician way of plotting circuits, which is drawing some points with specific potential. If you plot this, which is ground or earth, it means that this point here has a specific voltage equals to 0. And here, this point has a specific positive voltage, which is plus VCC. So you can actually plot here, let's say, a specific voltages that you can call UCC. And UCC equals to VCC minus V0, but since V0 is 0, UCC equals to VCC. And the question is about what is US here, US being equals to VS, again, because here, this point is at the ground. And how you're going to handle this, same way always, is try to plot voltages and plot currents if they're not here. So what you're going to do here is creating a current. So this is a current that I'm going to call I, okay? This current is going to flow through the resistor R2 and is going to arrive in this node. But now it can go through this and through there because of the node law. The problem is this VS branch is linked to nothing, which means that the current flowing in this branch equals to 0, which means that the current I is in fact flowing also through R1. So now what you're going to do is apply simply mesh law or apply the conventions you know. So here you see that US correspond to the voltage between this node VS and this node VS, but VS is also this node here that I'm going to call A. This node, everything here is at the ground. So what can you say about US equals to what, considering R2 and I?
Minus I times R2.
Exactly. Now, what can you say about UCC, considering R2 and R1?
Minus, in parentheses, R1 plus R2 times I.
Perfect. So now, what can you say is US so no. Up. Sorry, from this equation, you can deduce that the current equals to minus UCC over R1 plus R2. That you can substitute in this first equation. So you find that US equals to R2 over R1 plus R2 times UCC. Okay. And this is what we call the voltage divider formula. Why? In fact, so this is a pity that I don't have, you can't see my arrow. I have to check. Okay, sorry. So in this circuit here, you have UCC, which actually consider both R2 and R1. But the question is about what is US, which is only considering a part of UCC, which is only the part considering what is considering R2. So if now you go back to the final formula that we demonstrate, you see that US is just a portion of UCC. UCC is R2 plus R1, and US is just only considering R2. That's why you have the portion R2, which corresponds to US, over UCC, which is R1 plus R2. So this is a demonstration of what we call the voltage divider. How to divide a specific voltage. You have UCC, which is the voltage between two resistors. If you only consider part of this voltage, which is US, then you have kind of a proportional factor that you have to apply to know US. So in electronic, this is quite useful to starting from a specific output voltage, you can divide the voltage to be applied to other components with less voltage in your circuit. So this is called the voltage divider. And from now, you're allowed, if you see such kind of configuration, you are allowed to apply directly this formula without demonstrating it. If you want to demonstrate it again, you see it just take 2 minutes, but you're allowed to use it directly. Is it okay, or do you want me to step back or to repeat or to detail some part? Sounds good?
Yeah, it's good.
Yes, for me, yes.
Perfect. So now we increase a bit the problem by adding an extra resistor. As you can see, you have two other circuits. This is the same configuration, except that the resistors are not exactly the same. So we're gonna be smart here, and we're gonna make once the exercise, and we're gonna call every resistor differently. So let's see, R1, R2, R3, R4. So you do the exercise once, and then you just have to say at the very end, once you have the final formula, that R1 equal to R2 equals to R3 equals to R4 equals to R, or depending on the configuration, R3 equals to R4 equals to 10R, okay? But we're gonna do the exercise once. So again, this is what we are facing. Vs, VCC. This is equivalent to this, okay? Everything is at the ground. You can extend the ground here. This also could be also written like you can make a mesh from this, okay? This is linked because they are both connected to the ground. So this is your problem. What do you know from the exercise? You know that you're looking for a Vs voltage here, and you know that there is some VCC voltage, a known voltage here, but that's it, okay? So first things you need to apply is the mesh law. Go for it. Sorry, node law or mesh law, which are Kirchhoff law. There is no current from now in these circuits, so you're gonna apply them. So I'm just gonna change color, and let's call this the current I. Okay. Now I'm facing a node here. So I have another current here, and I'm gonna call I1. And of course, I have another current here that I can call I2. But again, to simplify your thinking and the solving of this problem, you can already apply the node law directly. So what will be the value of this current flowing in this direction as a function of I and I1?
I minus I1.
Everyone is you're all okay with this? Sorry.
Yes.
No, it's I think it's another I. So for example, I2 and I1 plus I2 equals I.
So is it I1? Are you okay with this? I minus I1.
I don't know, because there is another current coming from like before the resistance 4, right?
Yeah, but I'm just considering this node, A node.
Okay.
A node,
Yes, then.
I have this I have this I1, and I'm checking for the value of the current here, which is I1, sorry. Sorry. Okay, because what is entering in the node is I. What is going out from the node is the current, this current and this current. So I1 plus I minus I1, which makes I. Okay.
I just have a question. It
Yes.
might be kind of silly, but is like every intersection considered as a node, or can we have like an angle or something without?
Oh yeah, no, whatever. It's so each time you have multiple wires at some intersection, this is considered as a node. Here, B, you have another node. Here, it's a node, but again, if you face some, I would say, circuits which looks like something super complex like this, then this also is a node, F. Here, it's not really H. Here is not really a node because this is just kind of an angle. And this is the same wire, but you're allowed to put some letter in and say that you consider this point if you want. But by definition, a node is an intersection when you have at least, well, two wires having different current through them.
Okay, thank you.
So let's keep working here. So I was here. So now I know that the current here is I minus I1. Then I face another node at B. I have this part of wire which have to go to VS, but in fact it's linked to nothing, which means that the current here equals to 0, which means that in fact the full current I minus I1 is flowing that way. Okay. So now you have spread more or less the current through the circuits. Now the second step is to plot and draw the various voltages in between the terminals of all the dipoles. So let's start with R2. So you have a current up, and I'm going to consider the receptor convention standard, which is I'm going to put UR2, so voltages in the opposite direction than the current, UR1, UR3, UR4. Is it okay? If you are able to do this correctly each time, which means spreading the currents, applying the node law correctly, plotting the voltages in the right direction, considering the convention you pick, then you're done with 80% of the job. The rest is going to apply the mesh law, and that's it. And of course, you need to apply the mesh law correctly. So now everything is done on the drawing. You just have now to consider meshes and apply the mesh law. So I leave you with this. Try to work a bit from now with this scheme here, try to extract as many formulas you can with this exercise. The question is, what is Vs? And at the end, the result is going to be a function of R1, R2, R3, R4, and VCC, which means that all the currents, well, the two currents, I and I1 we introduced, are going to be substituted at some point. So your result shouldn't be a function of the current. So go and practice with this. We need to find Vs as a function of VCC, R1, R2, R3, and R4. So always the same protocol. I'm going to repeat it here. First, plot currents, applying node law. Then plot voltages between dipole, and then apply mesh law, Ohm's law. So you can have a lot of equations. So in this exercise, and this is always the case in mathematics also, but you need to consider your unknown. So the unknown is Vs. So you need one equation to get Vs. But to solve this Vs exercise question, you have introduced two other unknowns, which are the current I and the current I1. So at the end, what you need is at least three different equations. With three different equations, since you have three unknowns, you should be fine. If you have questions, feel free to let me know. I'm just going to write down the final result. So Vs equals to R2, R4 of So one thing which is quite interesting to notice, and is quite straightforward, is that here Vs equals to UR4, because this point Vs is exactly the same point than B. They're linked by a simple wire. So applying Ohm law, you can already say something about UR4 and Vs depending on the current, I and I1. Then the other clue is to say that you know that VCC equals to minus UR2 minus UR1. It comes from the mesh law, because you can consider a mesh with these three voltages. It can also be only the addition. You can see that VCC go from here to here in this direction, and you have like this VCC, and you have UR2 and UR1 like this, and they linked every terminals. So just considering these vectors, you can deduce this second equation. And then the last equation you need is going to come from the mesh, the big mesh you have in the middle. Let's pick some flashy color. Here we go. Here. So you apply mesh law in this big mesh, and then you have the three equations you need, and you should be able to find the final result. Again, if something is not clear, please let me know. But from now, it's just math. So if you have clearly understand the node law, the mesh law, this convention, receptor and generator convention, you have already 50% of the classes of this electrokinetic one part. If you already have the result, of course, you can move forward and do the last exercise with the different currents through the three different resistors. Are you able to find the result, or is it a math problem? Do you feel at ease with the equation solving?
I'm stuck because I can't get rid of I and I1.
So let's see. So this is R4 equals to I minus I1. VCS is equal to minus RI minus R1 I1. You apply the mesh law and you get, so I'm going to start from C and I'm going to say that it's going to be positive in this direction plus. So I have UR4 plus UR3 plus UR2 equals to 0. So I have R4 I minus I1. Since I know that I've considered the receptor convention, it's easy. You don't have to think too much because you know that everything is going to be positive when you're going to discuss the voltages. So it's R3 I minus I1 plus R2 times I equals to 0. So the idea is here from this equation to get I as a function of I1. Once you have this result, you go in this second equation to get VCC, or yeah, well, you have this, which is I as a function of I1. You have this one, which is VCC as a function of whatever I or I1. Once you have plot, use the result here in this function, and then you move another step up, and you should, so I as a function of I1, and you get this result here, either as a function only of the current I or only of the current I1, and using the result here, you introduce this here and you should be fine.
Okay, I'll try. Thank you.
The sum of you have the right result, at least. We're able to find or arrive at the very end of the computation.
No.
Nobody?
I wasn't able to either.
No.
So it seems that you have some math problems more than understanding the physics. Nobody was able to find the good result. So just to me to understand.
I think I have math problems because I have results with 2 R's or something like this, and so well, that's not what the result should be, I think.
Okay. So, all right. So with these pages, you have everything. Now, this is just math. If at some point you have math problem, then I can send you some exercise to practice your computation. But this is not coming from understanding the physical problems in electrokinetics. So just let me move to the last exercise. Last exercise is what are the different currents flowing through the different resistors. So we are going to handle again this exercise the same way we did previously. The currents are already a plot. Then you can plot, of course, the voltages. So you are gonna apply again the voltages considering the receptor convention. Of course, if you have time, you can demonstrate that using the generator convention, you will be able to find exactly the same result. But again, if you want to ease your life, this is an advice. It's easier to use for your mind to use the receptor convention. So now you have plot everything, and from here, the first thing you can say is, well, these three voltages are equal. So write the equation, and the last equation is the node law. So the node law is I equals to I1 plus I2 plus I3. And the other equation is UR1 equals to UR2 equals to UR3. So you can see that because this is the same voltages in between the two nodes A and B each time. But even if you don't see this and you see the different meshes, you can apply the mesh law in these different meshes. You have a meshes here. Let me put some color. You have a meshes here. You have another meshes here. And you have another meshes there, which is a large one. But you're gonna each time end up with the result, which is this 2, and here you have multiple equation. Again, you have 3 unknowns, and you have more than 3 equations, so you should be fine. Once you're gonna write using Ohm law what is UR1, what is UR2, and what is UR3, applying the node law, then you're gonna end up with the correct result. And that's it. So just I'm gonna give you the result here. And maybe you have noticed this, if even I go back to the result here on VS, on the denominator, you have all the combination you can have with the fourth resistors, sorry. And here VS is considering, in fact, the two resistors here are 2 and R4. And if you go back here in this, in fact, it's a current divider type of circuits, because you have a unique, a single current entering in a node, and you're going to divide it into 3 meshes with 3 different values depending on the different of the various resistors you're going to use. And you can see that in fact the current I1 depends on the two other resistors time the full current entering I over the combination, all the combination you can have with the different resistor. And if you go for I2, in fact, it's going to be the same R2. It's considering R1 and R3 at the numerator plus the combination, blah, 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 at the denominator. And for I3, same thing. So you're going to be R1, R2 plus the full combination time current. And again, it's math.
I have a question.
Yes.
In the other page, when you wrote the final result, is it VS in function of BCC?
Oh,
and
yeah,
not
yeah,
VS?
yeah. You are completely right. Sorry. Sorry. Yes, my bad. So for next time, please try to go through this two exercise, find out the right result. I hope it's only a math problem. So keep practicing your math. If you have some problem with math, please let me know or let your math teacher know so we can give you extra exercise to practice again. And that's it. So next time we will keep going through exercise number 4, which is only simple circuits. At the beginning, only considering one meshes, and then we're gonna consider multiple meshes in the second part of the exercise. All right.
Excuse me, could you just show the last page again? Because I didn't have to.
Oh, sorry.
Photo. Thank you. Perfect. Thank you very much.
All right. If you don't have any questions, we are done for today. Feel free to send me your question if you have some. If not, we will meet, I think, next what? Let's see. Next Tuesday morning. All right. If not, have a good weekend and see you next Tuesday. Bye-bye.
Thank you.
Thank you.
Goodbye.
Bye.
Thank you. Bye.
Bye.